Testing. Hello. So I have sort of the end here, which you don't understand yet, but I also have some handy dandy steps here, which I'll put on our website. And I broke this up into two columns. The invariance and the principal stress column is actually kind of short. The first thing is that the principal stresses always have a 0 tau. That's a shear stress tau. You could think of it as 3 o'clock and 9 o'clock on the two-dimensional Morse circle. In the current situation, we need to find 3 such principal stresses because we have a 3D problem. They will come out as they come out. It's an eigen problem, so you are comfortable with that, I hope. And you know that the eigenproblems, I think if you do it in MATLAB, they just kind of come out the way they come out, the way the robot wants them. What we want to do is order them as on a number line. So the sigma 1 will be the one that's the most right, and sigma 3 will be the one that's the most left, and sigma 2 is in between. So the most positive is sigma 1, the most negative is sigma 3, and the one in between is sigma 2. I'd like you to use these functions to actually plot them, to find the roots of the equation graphically. So what function is it? It's right here. It's, let me zoom in a little bit. X cubed minus invariant 1 x squared plus invariant 2x minus invariant 3. That's in your book. If you plot that, it's kind of misbehaving here. Wild loops, but you can see it's not perfectly vertical. Well, it's hard to see even. But anyway, where that crosses, those are the 3 principles. And this, of course, is sigma 1, this is sigma 2, and this is sigma 3. So I want you to do that, use the functions. And then I want you to do this check with the cofactors, the ABC. It's super cool. I don't claim to fully understand all of that, but it's essentially breaking up the eigenproblem into a series of 2 by 2s to make it very tractable, make it very palatable. And it's really step by step. I gave you those steps here where you'd have like a Q value, an R value. For instance, Q is 1/3 invariant 1 times invariant 2 minus invariant 3. 2/27. How often do you see that? Of course, those require the invariants. So the invariants are pretty straightforward. The first one is sigma xx plus sigma yy plus sigma zz. Those are from your original stress matrix. This is xx, this is yy, and this is zz. Second invariant is also a formula. A little more complicated, but still very doable. Third one's kind of a mess. I punted and just said it's the determinant of the stress. I'm not going to program that out, even though I think you all know how to do a determinant of a 3 by 3. I hope. So you need to get these stress invariants, and what that means is that there's a series of states of stress along 3 mutually perpendicular axes, which do not change irrespective of the coordinate system used. So it's kind of a fancy idea, sort of like I don't know what it's sort of like. I can't think of an analogy. I was going to say like hydrostatic, but it's not hydrostatic. It's different. How would you set up your programs? Well, this is very personal. How you want to do it is up to you. I like putting in the original stress matrix just as a matrix right here. Let me see if I could make the font a little bigger here for you. So yeah, just put it in as a stress matrix. Your transposition matrix is really kind of the hardest part of the whole thing. If you have a first rotation and a second rotation, and we talked about this in class, then the T matrix is it's second rotation times first rotation. I did it right, but I labeled it incorrectly right there. So it's second times first. You pre-multiply by the second one. If the direction cosines are given, as they are sometimes, like, it's super sweet if they're given, you just put those in. And then if the plane is given, that's the other method of the three. Remember, there's three ways of getting these T's, direction cosines. Then you need the handy expression for the T's coming from the plane. I explained that in class. The easiest thing that you could do is just say the new stress is the T matrix times the original stress multiplied by the T transpose matrix. That's one way of doing it. Do that. Go ahead and please do that. Another way of doing it is grinding these out with the clunky transformation equations like this. Sigma x prime is stress 1, 1, which is sigma xx times nx prime x squared plus sigma, etc., etc. So grind all that out. You don't have to grind out all 9. That's crazy. But grind out sigma xp, and then grind out tau net. That's the simplified equations from Budinas's book. I broke it up into term 1, term 2, term 3, term 4, just to keep the programming a little simpler. So term 1 is stress sigma xx times nxpx, sigma xy times nxpy, etc., etc. Term 2 is a little longer. Term 3 is there. Term 4 is just sigma x prime. Remember, there's a minus sign. Where's the minus sign? There's a funny minus sign in there somewhere, right? There it is. Minus term 4 squared. So term 1 squared plus term 2 squared plus term 3 squared minus term 4 squared. Someone's going to forget the minus, I guarantee it. Take the square root of that. So you need tau net. All right. What's on our list here? I've already gone into the other column here. So, like I said, the invariance and the principal stresses are pretty quick. I'll talk about this triple Morse circle next time. Let's go. Now we're moving on this column here. So sigma nu, the fastest way of doing it is T times sigma times T transpose. Get these, and then here, check sigma x prime via the equation, which is what I just said. And then find tau net via that equation in the simplified method section 2.14, right? All right, now there's also equations for Tx, Ty, and Tz. What are those? Those are 2 tau net. They are 2 the tau net. So when you're plotting this, and I don't know how we're going to do the plots, but we'll talk about it. You have a sigma xp value, and then a tau net xp. Well, it's on that plane. It's unambiguous. It's on that plane. Remember, sigma x prime is perpendicular to the plane. The net one is on the plane, but there's an infinite number of ones that are mutually perpendicular on that plane. All right, let's go back to our list. So the T's are the direction cosines to the tau net. The N's, the way I like to do it, and you don't have to do it this way, but you could use L, M, and N if you want, but I'm going to use L, M, and N for the direction cosines of the principals. So I kind of like N for just the regular old sigma normal on some plane. the t's for the tau, the direction cosines to the taus. There's an easy equation for that, so let's just take a peek at that. It's right here. T, direction cosine. There's x, there's y, and there's z. So there's three of them. There's just direction cosines to the tau net. All right. Now, how did I plot that point? Well, I broke this sigma x prime up into three pieces, x, y, and z. And it's really easy to do because I have all the parts. I have the actual sigma x prime, and I have the direction cosines. And remember, I'm using n's for those direction cosines. So that's easy breezy. And then sigma x prime point is the x part, the y part, and the z part. And that's what I showed in 3D here. I'll walk through some of the GeoGebra steps for you if you want to do it in GeoGebra. All right, let's go back to our list. Similarly, I'd like you to find the tau net three components. Remember, this is a special tau net. It's from the simplified method part. Get the x, the y, and the z parts of that. And again, that's super easy breezy because I have tau net and I have the three direction cosines to the tau. And then that point is plotted here. And that is mutually perpendicular to the sigma, as you could see right there. What if you need the third axis? Well, first of all, I'm going to ask a thought-provoking question, hopefully. What is the tau perpendicular to these two? The tau. And the answer is the tau is 0 perpendicular to these two because this is tau net. So there is nothing perpendicular to it. If you want that third axis, this is slightly... I don't know if it's hard. I guess everything we do is hard. I drew it as a little yellow axis right here. It's perpendicular to the sigma and to the tau. There's that little yellow one. You can see it right here. And how did I get that? It's a cross product. So it might be a long time since you did a cross product. I'll walk you through that in a minute. So this I do want us to do here, and this is really not hard at all. It's just a little tedious. So find tau z prime x prime. Now your author specifically calls it z prime x prime instead of x prime z prime. So that's what I did here, and it's just one more of those clunky transformation equations. So what does that look like? It's just in here, tau z prime. So the first one, x prime, y prime, is that, and the z prime, x prime is that. So it's just one of those clunky transformation equations. Why do I want those two? Well, the x prime, y prime squared plus the z prime x prime squared, take the square root of that, that should be a minimal check. That should be tau net. If that doesn't work, you screwed up. The next part is super cool. It took me a little while to kind of see what he's doing. I did not come up with this. Your author did. What he's saying, okay, well, wait a minute. Here's another check. How can we go back to XYZ world from the new coordinate, the new stresses? So I mentioned this in class last time. If you want to go from the alternate coordinate system back to the original, then you start with T transpose. You pre-multiply by T transpose. So let me go slowly on this one because this is a little thought-provoking. So sigma nu is a 3 by 3. So let's go find sigma nu. Sigma nu is a 3 by 3. What your author is suggesting is to take this number here, which is sigma 1, 2, and this one, which is sigma 1, 3, or tau, tau 1, 2 and tau 1, 3. This stress and this stress. And to put those in with a 0 in the first term. Now, why is there a 0? All we're doing is breaking up this tau. We're breaking up the tau. I can't remember. This one is tau, I think, right? Yeah. So we're just breaking that one up into the two components within the plane. Perpendicular to that plane, this tau has no component at all. I know it might sound a little funny when I'm just saying it, but it's this. So there is no third component to those taus. So all I'm doing is taking sigma nu 1, 2 and sigma nu 1, 3, the first row of the nu matrix, and I'm pre-multiplying T transpose with that vector, and I should get tau xyz check, which I just did over here. I got tau net in the x, tau net in the y, and tau net in the z. And those are just the components of that special tau net. So that's a super cool check. Super cool check. Real quick, how do you get that third axis if you ever need that yellow one, which is mutually perpendicular to the sigma and the tau net? It's a cross product, and like I said, it might be a long time since you've done a cross product, so I will walk you through it here. It's not, well, I mean, on the computer it's not that hard. You have to put in the vector that defines sigma x prime, but we already have that. That is nxpx, nxpy, and nxpz, those three. And you have to so it's like a unit vector in the direction of the sigma. And then you do the same for the tau net vector, and here it is and that should be the t's. So the tx direction, you can call it just tx, ty, tz. I just called it tx direction cosine, tx, ty direction cosine. Again, it's like a unit vector along the axis of the tau net, and then I take the third vector, which is just the cross product of these two. So it's sigma x prime vector cross tau net vector. Now, if you're doing this by hand, which is doable still, it's what is it? It's the determinant of I think I wrote it in here in your notes. It's the determinant of, I guess I didn't write it in here. It's the determinant of ijk, and then the next row is, that's a row across, then the first vector is a row across, and the second vector is a row across. So that's a little clunky to do a cross product by hand. You could do it in MATLAB. You could do all of this in MATLAB too. So that check is kind of exhaustive, but not exhausting, I hope. Now I want to talk a little bit about the Morse circle one more time, and why is this constructed the way it is. What we'll find is that all states of stress that are allowed can be either on the perimeter of these circles or in this body between the circles, in this kind of area between the three. And as we move through the course, we'll do some failure theories and get into that. So I'll get into this construction of the circles and like a little tutorial for GeoGebra in the next video. Okay, thank you.